Hi, I'm Fabiola Robles.
Hi, my name is Rose Sanchez Irizarry, and in this video we will be presenting our project Doppler Effect Simulator.
The topics that will be talked about in this presentation are indicated here. We're going to be talking about the motivation, a little bit of theory, what is the Doppler effect, the objectives and methodology, phase 1 of this project, and the expected outcomes. This project is actually phase 2 of a previous one that will be talked about later on. Our motivation came from asking ourselves, how can we use our abilities as engineers to facilitate learning about sound wave properties and the Doppler effect, but not only for K-12 students, but for everyone.
Sound waves are longitudinal waves caused by vibrations moving across a medium.
The volume in a sound wave can be represented in a graphical way by the amplitude of a sine wave. The lower the amplitude of the sine wave, the lower the volume will be, and vice versa, the higher the amplitude, the louder the sound will be. The pitch with which we hear the sound wave is defined by the frequency. The lower the pitch, the lower the frequency, and the higher the pitch, the higher the frequency.
The speed of the wave can be calculated using this formula. Here, our source of sound will be the ambulance. Now, as the source moves away from the person perceives a low frequency. But as the source moves towards the person will be experiencing a high frequency. What is the Doppler effect? The Doppler effect is a common natural phenomenon that occurs to all harmonic waves. It is experienced whenever there is a relative motion between the source and observer. The frequency at which the sound is perceived can be calculated using the following formula. In this picture, we can see how the sound waves behaves as the car moves from point A to point B. Did you know that police radars that determine the speed of the vehicle uses this concept? In this case, the speed detector bounces off microwaves in the direction of a moving vehicle, and then detects the waves that are reflected off of it. The waves then are shifted in frequency due to the Doppler effect, and using a formula, the beat frequency between the microwaves and the reflected waves provide the speed of the vehicle. Assuming that the eye is the listener and he is in a static position, when the black dot moves away from the eye, the wavelength of the sound source is shorter than the listener's, but the frequency of the source is higher than the frequency of the listener's. As we keep assuming, the listener remains in a static position. When the dot moves towards the eye, the wavelength of the listener is longer than the source's, while the frequency of the listeners is lower than the source's.
Our objectives revolve around utilizing the MSP430 and Energia to implement a Doppler effect simulator, with the purpose of making the concept easier to grasp for students in the grades K through 12. Our methodology followed the flowchart shown. We firstly focused on learning how to program the MSP430 using Energia and then proceeded to modify the frequency to simulate the Doppler effect. Then we incorporated the 3 buttons that will simulate the different stages of the Doppler effect as well as a button with an original sound as reference. 4 button functions will be as follows. The first button will be for the actual sound, which will serve as a reference. The second button will be the slow speed, where there is a tiny continual increase in volume and pitch, simulating the sound source approaching slowly and stopping halfway towards the listener. The third button will have the middle speed setting, where there is a fast continual increase in volume and speed, simulating the sound source approaching the listener and stopping right next to them. The fourth button has the fast speed setting, where there is a fast continual increase and decrease in volume and pitch, simulating the sound source approaching the listener and passing them by. For the simulation to have a visual aspect, we will add an LED road that will light up showing the path the sound source has traveled through. Once these aspects have been completed, we will combine them into a display. We chose the MSP430 due to its versatility and capacity to accommodate all the features we will use to create the simulation, since we will be using a programmable gate amplifier in conjunction with LEDs and buzzers as well as the buttons for the different simulation stages. During phase 1 of our project, we created a GUI utilizing MATLAB, where the speed of the music played changed according to the button pressed, simulating how the music would be heard when the object emitting the sound was static and far away, close to the listener, right in front of the listener, and right next to the listener. On phase 2 of this project, we want to use the lessons learned on the previous phase and apply them to the second phase, which involves implementing the simulation with the MSP430.
Finally, for our expected outcomes, once the investigation is finished, we expect to prove that the MSP430 Ti Launchpad can be a significant aid in teaching about wave properties to students from kindergarten to 12th grade. We also expect to have a designed and a physical prototype of the Doppler effect simulator, developed using the MSP430 Ti microcontroller. And for our final outcome, we expect to have an interactive display that creates the complete Doppler effect experience, to later showcase at C3 Tech, a center of science and technology in Caguas.